Hi folks, Harry Frank for FX PhD. We're kicking off week 1 of our expressions bootcamp, and I'm excited to do this. Now, a number of years ago, I released a training series on After Effects expressions. In fact, 2 of them. They covered quite a bit. Now, in the time since I've done that, I've learned quite a bit. Expressions actually have changed a little bit. At least they've added new features. And I've also just gotten a better understanding and found better ways to teach them. So I thought it was about time to revisit the idea of expressions. Now, that said, you don't need to know anything starting this class. This is really to sort of start from square one, or I guess square zero, really, if we're doing expressions. And we're going to move forward. So this will get into some really tricky stuff, but I want us all to start in the same place. So if you're an experienced or intermediate expressions user, this first couple classes might move a little slowly, but it's always good to go back to basics, and that's what we're going to do. So the first thing we're going to do is actually something a little tricky, which is creating this second hand. Now, a second hand is a pretty novice place to start, but I thought I'd add a little bit of a twist in here, which is having some realistic behavior where the second hand actually moves but wobbles at each second mark. And this is done completely without keyframes. And one of the reasons I wanted to do this is this offers a good introduction to expressions, because second hands and minute hands are a very easy place to start. This is just mostly some very simple math. But this also answers a question of why to use expressions. And I've seen this debate before, and this is a perfect example of why to use expressions. I've seen the debate of, if people use expressions, things tend to all look the same. But expressions really should be a time saver for you. They're not the complicated way out. They're the easy way out. In the case of making an exponential decay, there's absolutely no way I would want to manually animate this, and it would never look correct. Now, other things like, wiggle functions and all that tend to look alike. Yeah, I agree. Like, let's animate our things, when animating them manually is feasible. But when expressions are a great alternate, or a great way to save time, I highly recommend going the expression route. And we'll see lots of ways that expressions make the impossible possible, or make things just go a heck of a lot quicker. So that said, we're doing back to basics right now, so let's just cover the basics of expressions, make sure we're all on the same page. So I've got my little getting started comp right here. Whoops, I bumped F12, sorry about that. Okay, so I've got this little pattern in the background here. This is 60 lines all the way around in the circle. Pretty straightforward. We don't need to know how to do that. That's just there. It's a shape, a shape layer that I made. What we'll be paying attention to is this little second hand right here. And we're going to make this thing move around in different ways and learn different functions of After Effects expressions. So, oops, my stylus seems to be stuck. I hate when that happens. Okay. So let's look at a parameter here. Any parameter, well, I shouldn't say any parameter, many parameters are controllable with expressions. What is an expression? Let's not even get too far. Let's actually define what expressions are. So when we refer to expressions in After Effects, expressions are a JavaScript-based programming language that we can use to control different parameters in our After Effects layers. Expressions can either control parameters entirely, or they can work along with the existing keyframes. And I'll show you different examples of how to do that through the term. Certain things cannot use expressions. There's a handful of things. Masks cannot use expression. Well, I actually, that is not true. That's changed recently. You can link masks together with expressions, but that's about it. Other things like level histograms or anything with fairly complex data is not accessible via expressions. And as we come across those, I'll try to point them out. But most parameters, anchor point, position, scale, rotation, opacity, or even effect controls, like exposure controls. Anything with a numeric readout is always going to be controllable with an expression. So that said, do you need to know JavaScript to use expressions? And the answer is no. You don't need to be an expert in JavaScript, but you need to understand one thing before we go anywhere. And this is always going to be my golden rule here. If you ask the question, can expressions do this? Ask yourself this question, or actually tell yourself this statement, because this is not a question. This is a statement, and it doesn't have a period. So that's going to bother me. Let's put a period in there. There, period. Expressions cannot do what keyframes cannot do. Or in other words, expressions can only do what keyframes can do. So the whole point of expressions is to automate simple tasks, things that would be repetitive or things that would just be very tedious to do, like matching an angle between 2 points. If I'm moving things around, I can match the angle between them, things like that. And we'll see lots of different examples. So in this case, I'm going to move this and have it stop at each second point. And then at each second point, I will have it wobble just a little bit. Now, if I were to manually animate that, this would take me 2 days. I could, I guess, copy and paste keyframes or that kind of thing. And then the client comes along and asks, well, I want the clock to actually speed up at some point and then slow down again. Then, let's just use expressions. So let's get started. We're going to look at a parameter here like rotation. Rotation is always a good place to start because this is what we call a scalar property. It only has one value that defines what it is, and this is a good place to start. Other properties get a little bit more complicated, like position. Position is what we call an array. It has two properties that define what it is, x and y, or if it's 3D, it would be x, y, and z. For scale, it has x and y scale. Those are arrays. There's two different things in there, and we always have to account for both. We're not going to go that far. We're just going to worry about rotation right now. Now, expressions can be very, very simple. And before we get very deep, we're just going to do some very basic math here. So to create an expression, we'll hold down the Option key or Alt key on the Mac OS and click on the stopwatch. I think you can also go to Animation, add Expression. There's a weird shift something, I don't know, whatever that is. So just Option click. And you'll see a number of things pop up here. This first one right here enables or disables the expression, which will turn on if you actually have an expression error. The expression will be disabled. And we also can see that there's an error there, and if you want to see what the error is, again, you can actually, and don't discount that. People, sometimes you get an error and people just say, I got an error and I don't know what the problem is. Actually read the error, because often, not always, but often it gives you a pretty good idea of what's going on. Let's put something in here that's not going to give me an error. I can just put a number. Let's put a number like 5. The value becomes 5 because I put 5 in there. Pretty straightforward. Hey, not a whole lot of JavaScript, huh? So this next one right here allows the expression to actually be graphed in the graph editor. So if you want to see what's going on, especially if this is animating over time, this is a static value, so we're not going to see a whole lot going on. But if you want to see it actually charted out, you can see that we've got a value of 5. This is something that is called the pick whip, which you quite possibly know what it is, but if you don't worry, we'll cover that quite a bit detail. And this is our handy expressions reference. This actually comes in pretty handy if we forget how things work, like if you forget how to loop properly, or if you forget, or you can actually just pull up things pretty quickly that you'll use often, like seed random. These are all things that we'll get to, so if you don't know what they are, don't worry. Just covering the little buttons here that are visible when you are using expressions. So to make this thing move, we're going to use something that we'll use a whole lot, which is the word time. Time is a very, very useful word. Now, that said, let's talk about these reserved words. All of this stuff in here, these are all reserved words. These are words that are used in the expressions programming language. So things like linear or ease or RGB to HSL, or width, height, duration, that kind of stuff. As we move forward, remember that these words are all reserved and can only be used for the functions that you see in here. So time is a reserved word. The word time in an expression is equal to the playback time in seconds. So if I set the current time to 10 seconds, you'll see that the value is 10 degrees. Pretty straightforward. Again, back to basics. So how do we make this a little bit more useful? Well, as I mentioned, we'll be using basic math. So there's nothing stopping us from adding something to this. So I could say time plus 10 or time minus 10 using plus or minus to offset it. In fact, that is often used to offset things. It's very common to sometimes offset things by 180 degrees when we're working with degrees. Or if you just want to shift it ahead or behind, that's a good way to do it. But in this case, we're going to multiply. Because, well, I've got a minute-long composition here, and if I go to the very end, you can see this is moving 1 degree per second, and at the very end, we're going to get to 60 degrees. That's not what we want. We actually want one full revolution. We want 360 degrees. So I'm going to set this to use a multiplier using the asterisk. Time times 6. I'm using 6 because that's the multiplication factor I need, basically, to get 360 degrees when we're moving 1 degree per second. Over the course of 1 minute, I need it to move 6 times as fast. So you'll see at the very end, and actually we're not quite to 1 minute just yet. What am I using as my, I'm using 29.97. So at the very end, I'm not quite to 1 full second, and the revolution is not quite to 360 degrees. And that's exactly what we want. So there, we've made it automated, and it is moving on its own without keyframes. It's almost magical. So now let's get into linking things together. Let's say I have another hand that I want to follow the movement of this, but to move even quicker. So let's say we have, and actually let me just borrow a layer from here. This is often like a milliseconds hand or something. Let me just get rid of this. So I've got another one right here. And there's a number of ways I can do this, but what I'm going to do is have this hand look at the rotation of this hand and move faster. So I will select the rotation of that layer, just hit R, and in this milliseconds hand, I'll option click and use the pick whip. This is the pick whip right here. I don't know if the pick whip is truly understood. Some people call this like parenting, or parent this parameter to another parameter. This is absolutely not parenting. All this thing here does, this little squiggle, is it's a quick way to enter code from whatever we target. So if I were to have this layer look at this layer, there's a certain syntax that I would have to use to look inside this composition, inside this layer for a property called rotation. And there's a certain way I have to spell that out. And once you do it over and over and over, you'll get a pretty good feel for looking inside this comp for a layer called second hand. See if I can do this all from memory. Second hand, and looking at, I think I just type rotation. Hey, look at that, I got it. But you don't always, you're not going to have that memorized. So a good way to do this is just to use the pick whip, and I'm going to target this parameter, and it's going to enter all that code for me. So it's not parenting, it's entering the code for whatever I grab and target. So you notice that if I just drag down here and just select a layer, it will just enter the layer. There's no property associated. And this is going to give me an error because it's just saying, look in this comp for a layer called shape layer 1. Okay, well, I said, great, I found it, but I just found a layer. I need a number or something that tells me what to do. We have not done that. We've just given it the layer name, or just the layer itself. So if I pick with this, there we go. Now it adds a little redundant thing in here where it says transform.rotation because it's rotation is a part of the transform group. This is kind of a legacy thing because it always didn't have that. And I mean, you can leave it. I tend to get rid of it. I just use rotation. So this comp, layer, second hand. So it's looking at the second hand and using rotation. It's good to start getting familiar with this rather than just blindly looking at this as some sort of language you don't understand. Understand the structure here. It's always going to look, when we're looking at a parameter, it's going to look in a specific comp. It doesn't have to be this comp. It can look into another comp. But we're looking inside this comp at a layer called second hand, which has to be in quotes inside parentheses, and rotation. We can also call out layers by number. So if I get rid of the quotes and then just inside this layer, I look at layer number 2, I can look at the rotation of layer number 2. Or I've got a third layer here, I can look at layer number 3. You don't always want to do that because, well, layers often change as you're animating. But this is something that becomes handy later on, especially when we start looking at or duplicating layers and using what we call the index, which is the layer number. But we'll get to that later on. In fact, let's just hit undo. There we go. So we're looking at the second hand. So just like we did before, we can use multiplication. So I can multiply this times 6 and have this move 6 times as fast or 60 times as fast. Now, 60 times fast every second, as this moves from 1 second to the next, it's going to complete 1 full revolution. So that's just basic math, basic syntax, and basic pick whipping. That's a lot of expressions. A lot of expressions are just that. In fact, I would say almost half of my expressions I use in After Effects are really just using the pick whip and offsetting things different ways using very simple math. Okay, so let's take this a little further because, you know, I could just as easily animate this from 0 to 360 without using expressions, just use keyframes. So let's do something that would be a lot more difficult, which is have the second hand stop at each second point. So this is going to get into rounding our values, and this will be our first mathematic function we'll use. So in our JavaScript section here, you can see we've got something called math.round value. So the way these work is that as we feed a value into this function, so math.round is the JavaScript math function that we're using, and inside the parentheses is the value that it's going to round. So if I put in here 2 point something 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 something, it's going to round it to the nearest integer value. So if it's 2.73 and it rounds it up to 3. If you'd like to control which direction it's going, there's actually 2 more very handy ones that are quite possibly used even more, which is math.ceiling or ceil and math.floor. Floor rounds the value down, and ceiling always rounds it up. In this case, I think math.round is just fine. So we're going to round the time value as time progresses. So if I set this to math.round.time, it is simply going to round it to the nearest integer, and that's not what we want. Just like we did before, we want each progression, all going with the motion of this, multiplied by 6, because this is 6 degrees right here. 6 by 60. So instead of having this progress 1 little tick like that, we want it to go 6. So 1 degree, 6 degrees instead of 1 degree. So again, math.round.time times 6. Now the second hand is going to stop at each second marker. Very cool. Okay, so now let's do something a bit more complicated. And this is going to introduce some new concepts, and even though some of this might be a bit getting ahead of ourselves, none of it's actually that complicated, and we'll go through and discuss all of the things that we're going to do in detail, so I don't want to leave anybody behind. So we're going to get into one new concept, which is using variables. In expressions, variables are just a way to store information and take large amounts of data, even or large amounts of syntax like this, comp layer, second hand, dot rotation time 60. Things like that can simply be stored in a variable. So I can, instead of using that every single time I want to access this value, I could set this to something like n. So I could say n equals that, and anytime I want to access this comp layer, second hand, rotation time 60, I could just use the letter n. Now, the thing with variables is we always have to use a semicolon at the end. It's just a JavaScript thing. Don't think too much about it. But anytime afterwards we want to use n, we can just use n. I could use n plus n, or n times, or plus 8, or whatever. It's just a way to assign values. It's also an easy way, if we look at this expression right here, it's also an easy way to make things adjustable. So in this case, and we're going to go through all this stuff. I know this looks pretty scary and crazy down here, but we'll actually use a simplified version of this. But it's also an easy way to put up front things that need to change or be sort of adjustable. So in this case, like that, and something called an amplitude, and this is how much or how far that wobble is going to displace. The frequency is the speed, how fast it's going to wobble, and the decay is how quickly it is going to decay to zero motion. So rather than poking around in this equation right here to add different multipliers to sort of raise or lower certain values that I'd like, I can use those variables, such as frequency and amplitude right here, strategically placed so that we can easily change it without having to jump inside our more complex equations. So that said, let's talk about what's going on here. So we want our second hand to progress once every second. That's cool. But then from there, we want to have a decay that happens at each second. Pretty tricky. How are we going to do that? Well, the first thing we're going to do is use both regular time that progresses normally, uses decimal places. So we have a very detailed time that we can work with and a rounded time. So let's get that far. So we've got our rounded time here, and we'll have sort of a unrounded time. So let's get that far. Okay, so let's establish these two values. So I've got a rounded time and normal time. So my first variable, I'll just use lowercase r time equals the rounded time, and set my, or close it off with a semicolon. And for unrounded time, I'll just use lowercase t, and this will be equal to time. So this way I can always use just t instead of the word time. Now, if we think about what we want to happen in this wobbling second hand, I want a value that I can use to trigger this sort of decaying wobble. So if I have a value that repeats each second and has a changing value that I can use at each second, this is a good way to sort of drive a repeating wobble. So the first step is just to get something that repeats and changes value every second. So I've got these two values here. We've got the rounded time and normal time. If I say t, in fact, I don't know if I'm saving you any confusion by assigning that. I'll just use time. Time, which is a regular time, minus the rounded time, is what I'll put in here for right now. This isn't going to be our final value, but just so you can see what it is, and if I clicked graph here, we can see we've got this repeating value over and over. So this will start at 0 and increase over and over. So we've got our repeating value that changes each second, and we can use this to drive that wobble. Now this is just going to be essentially mapped to the wobble amount, this value right here. And you can probably think that we're going to assign this to a variable. And this is sort of going to be a time factor. So I'll just call this t. That's a good way to use these together. Now, let's get into some new JavaScript math functions here that are very, very handy. Now, what I'm going to stress is that you don't necessarily need to know exactly what's going on with these when you use them, such as math.sine. I know that's trigonometry. I know that sounds daunting, and especially jumping into it on our first lesson, but it's very handy to have because this is an oscillating value that goes up and down. So when we want things to sort of oscillate back and forth or rotate back and forth or move up and down, sine and cosine are two very, very good ways of doing this. So let's just see how a basic sine function works. Actually, let's go into, I have another comp here that I have just a sort of raw exponential decay. And let me duplicate this, turn the original off, and we'll start from scratch on our rotation here. Oops, sorry. Okay, so in my second hand, I'm going to type an expression that says math.sine. And in parentheses, just like we did with math.round, inside parentheses, we have to put the value that we're taking of the sine value. Now again, I'm not going to go into the trigonometry of y. You either know this and you took it in high school, or it doesn't look familiar at all. Either way, it doesn't really matter because what we're interested in is the result. If you want to read more about it, just go up and look up sine and cosine on Wikipedia. But like I said, it doesn't necessarily matter. What you do want in there is some sort of changing value, because if I just put a static value in here, that's not going to do us any good at all because it's not going to change over time. We want time to change over time. Let's ungraph that. There's our sine wave. So it goes up to 1, back down to 0, down to -1, and back up again, over and over and over. So it's just going to oscillate 1 degree back and forth infinitely. Now, that doesn't do us a whole lot of good if it's just going to go 1 degree. But again, like we've done before, I can multiply this. So instead of going 1 degree, it's going to go 30 degrees in each direction. And again, I could graph that, and you can see that the sine wave there. Now, I briefly mentioned cosine, which is just another. It's actually the same thing, but it starts offset by 180 or by 90 degrees. I'm sorry. So if I say cosine, notice that it starts in the middle. Right here, it starts at 1, and cosine. Or I'm sorry, sine. Cosine starts at 1, sine starts at 0. That's the only difference between them. Otherwise, they are simply offset by a quarter of a full wavelength here. But again, all it does is move it back and forth. As an animator, that's all you're concerned about. If this, especially if this doesn't look familiar or looks intimidating or scary, all it does is move back and forth, or change the value up and down from 1 down to -1, over and over and over and over. So if we want this to move faster, more quickly, more frequently, we want time essentially to move faster, because we're using time right now, and time moves at 1 per second. So if we want more, we want this to move quicker, we want to amplify how quickly that moves. We want to amplify time by multiplying time. This is one of the things when I show this that can be a little bit confusing, because we're multiplying out here to increase the range of motion. So we're amplifying the range of motion on the outside of the parentheses. And the inside, we want to multiply time to amplify how quickly time is moving. So now this is going to move more quickly. If I say this is 20, it's going to even move more quickly. Now, instead of hopping inside my equation to change these things, it might behoove me, might be more of a programming-friendly way of doing this is to assign a variable. So I can say the frequency is equal to 20, and then my frequency is plugged in right here. Frequency is equivalent to 20. This just is a more friendly way of doing things, especially if you're distributing these or saving these or even using them later in something that you program. I've done this plenty of times where I've programmed an expression, I come back to it, and I couldn't even understand the actual expression that I apparently at one point understood. So this is a nice way of sort of documenting and making your expressions more user-friendly. They're also a lot easier to read. If I can say, oh, here's a frequency that probably makes this move quicker. I don't need to dive inside here and take this thing apart with my brain to figure out what's going on. So how far it moves would probably be something like an amplitude. So instead of using 30, we'll just use amplitude. So this is going to just swing back and forth over and over and over forever. This will never stop. In fact, let's just turn off. Well, maybe motion blur actually helps. There. So it's just going to move back and forth. So we want something that actually decays over time as well. So what we can do is, well, I guess we could do this either way of multiplying it or dividing it. But if I divide this by something that increases or decreases over time, I should say. Well, if I divide it by something that increases over time, it will slowly come to a stop. That's what we're going to do next. So we're going to divide this whole thing by something that'll put on the other side. So before we get into dividing and doing more math over here on the other side, this brings up an interesting point that is worth covering right now, which is the order of operations. And you probably remember this from your grade school math class. And this, it's the same in After Effects. We just have one added thing here, which you probably didn't have in grade school. If you did, I'm very impressed, which is JavaScript math. So first things that are always calculated are things that are in parentheses. So in like our example that we're working with right here, I have time times frequency inside parentheses. So that's going to be calculated before anything else in this line. Even though JavaScript is reading this thing from left to right, it will lead the whole thing left to right and then take into consideration, all right, we've got this in brackets or parentheses. So that needs to be calculated first, and then we'll take the JavaScript math function of that, and then we'll take this whole thing and then multiply it by this amplitude. So this is very important to understand because you can have very different results based on the order of operations and how things are calculated. Even though it goes left to right, it doesn't calculate left to right. So brackets or parentheses are always first, and then JavaScript math functions like we've covered. Math.round, math.floor, math.sign, math.pi, whatever. Anything that's a JavaScript math function will be calculated first. Then multiplication, division will be calculated after that. And then lastly, addition and subtraction. So anything that is addition or subtraction will be calculated very, very last. Which sometimes is, it's sort of handy to have that, but I still kind of always recommend using parentheses to sort of organize things. And that's actually what I'm going to do. I'm going to put this stuff in parentheses because I want to make sure that this calculation right here is divided by another calculation over on the other side. So if I take this whole thing and divide it by another value, in fact, what I want is an increasing value. So as this increases, this decay will slowly come to a stop. Now, I could use something like time, but that's not exactly what we're going to need. What we want is something that is more exponential. This is just the nature of how things, with sort of spring motion, how things tend to behave. And rather than just using time, which is basically a straight line, a straight diagonal line, and actually also prevent this actually at the very first frame gives us a problem because time at 0 seconds is 0. So if we use time on the very first frame, we're going to get an error because we're dividing by 0, and we can't do that. That's an illegal operation. So I'm going to use another JavaScript function, which is an exponent. We're going to take the exponential value of time. Now let's take a look at this. Now we have a decreasing exponent. And actually, let's duplicate this and just isolate that exponential value so that you see exactly what is going on here. So exponential values start low, and you can see that they slowly start to increase. And then over time they get extremely large, to extremely large, very things only expressed using scientific notation. And this is what we want. We want something that starts small and exponentially increases, and that's exactly what this function does. Math.exp takes the exponential value of whatever is in parentheses. In this case, it's time. Now, if what I said makes absolutely no sense, you're probably right on track, because I really didn't explain what exponents were, and I'm kind of assuming that you are. And exponential functions are kind of weird. Like when we say 2 to the third power, that's pretty straightforward. 2 times 2 times 2, that's 2 to the third power, which is 8. But when we're dealing with an exponential function, we actually are kind of dealing with a weird and kind of arbitrary value. If I say, what is the exponential value of 1? This is essentially when we're using exponential function, we're saying a number e to the x value. So e is our exponential value, and x is this number right here. And that value is actually 2.7. It's actually 2.718281828. I don't have that memorized. If you want more information on this, you can look up the Wikipedia page where we talk about e to the x, and that e number is 2.7.1, etc., etc. So essentially what we're doing is using 2.7 times 2.7 over and over 2.7. And I could do this over and over, 2.7 times 2.7 times 2.7 times 2.7. And, oops, I have an extra asterisk out here. And this is going to start getting large and even larger as oops, I'm missing one right there. We can see we've got a great number of revolutions right here. So as this increases over time, that's essentially what we're doing. It's just 2.7 to the first power, 2.7 to the second power, and slowly increasing that over time. I honestly can say I don't know why it is 2.7.1, etc., etc. I'm sure there's some real reason that I don't really care about. But what we're more concerned about, we're concerned less about the exact math that's going on here and more about what's happening, is that we have a value that starts small, is never 0, it's always 1, which is good because you don't want to divide by 0, and exponentially increases over time. And that's exactly what we want. So, oops, I'm zoomed way in here. So this function right here is what we are dividing by. So as this increases from a very low value and increases to a higher value, just due to the nature of math and dividing, the whole output of this whole thing here is going to start large and oscillate, but eventually come down to 0. So that's what we get when we mix our sine wave and our exponential decay. And we're mixing them together by using division. So again, if I eliminate this, in fact, let's just delete that. That's our sine wave. This is our sine wave divided by this increasing value. And I need to make sure to put one bracket there, or one slash, because 2 slashes means a comment, and a comment doesn't do anything. So this is our exponential decay. So if I play this, this looks like a nice, invisible because the layer is off. There we go. There we go. And that is our exponential decay. It's just that easy. Now you might have seen this with other stuff in here, like the frequency, and then multiplying this times 2, and then also multiplying this by either the JavaScript function math.pi, or you can manually type in 2.14159.265. That's as far as I remember it. And the reason for that is that this actually makes the oscillations per second evenly divided. In other words, this frequency here, 20, if we multiply this by 2 times pi, actually becomes, this number here is the number of wobbles per second, or oscillations up and down. If you aren't necessarily concerned about that, which I don't think it's that big of a deal. If you either want it to go faster or slower, you can increase or decrease the frequency. But that will make programmers very itchy and not able to sleep if this frequency doesn't actually mean something specific. So just know that right now, this frequency just means faster or slower, but it doesn't necessarily mean something specific in terms of how many oscillations per second. So if that doesn't bother you, then fine, great. If it does bother you, then you can make this multiply times math times 3.14, and we'll be pretty close. Oops, math 2 times 3.14, and then we'll be pretty close to oscillations or frequencies per second. So right now you can see it's going really fast, and if I zoom in here, we can see we probably have about 20 oscillations in there for 1 second. So I guess I'll leave that, and I'll just set this to 8. So we've got our wobble going on here, and we've manually constructed this. I think we're doing pretty well here. So let's jump over to our getting started here. Actually, let's copy and paste this to our second hand. So we had this value. Oh, sorry, I'm jumping around here. I'm probably driving you nuts. Let me just get my thoughts organized. And let's move this millisecond hand down here, and let's just get things organized. Okay. So remember, I added these variables here just to make things a little more simple. So I always do that. I always put our initial variables at top, and then additional calculations that we need to do below that. And you're free to put as many returns in here as you want. Also, spaces in between things are just fine. Spaces are generally ignored and make things look a little bit more, well, I think they make them easier to read. So over time, we have this time factor right here. We're just using raw time, and that's why it just starts at the very top from frame 0 and just goes down to 0 and does not repeat. That's because this time is a fixed value, or I shouldn't say it's a fixed value, but it's a constant value. It's going to go from 0 to 60 in this comp, and that's it. It's not going to repeat. And in our wobble here, our second hand wobble, we want this to repeat over and over. We want it to repeat every second. So remember, we made this rounded time and regular time, and we said t is equal to time minus our time. We had that increasing value that repeated over and over. So in here, I'm going to swap out time for t and time for t right here, because it's time for t. And, oops, I don't want to auto keyframe. Now, I've got a very, very high amplitude here. Let's set this to something like 2, and let's leave that at 8. Now, we've got our vibrations happening each second, and we need this thing to just sort of progress one little tick each second. So we will add to this whole thing. So I'm going to take this whole thing and put it into parentheses. Notice that this sometimes makes parentheses double up next to each other, but this is, I'm printing parentheses over this whole thing here. And to this, I will add our time. So this is the rounded time. And that's that rounded time that needs to be multiplied by 6. Now, it's getting there. It's progressing, it's moving each second, and it's got some wobble going on. But here's the real problem. I'll sort of cut to the chase. The decay that we've got is, well, if you remember, this was our raw decay. Look how long this decay actually takes to get down to 0. It takes, well, near 0. Actually, never really hits true 0 for quite some time. But the decay is a good 5 or 6 or 7 seconds long. So we need to be able to control that decay. So up here, we're going to add one more variable called decay, and this is going to go on the exponential math side. So we'll set this to something like 5 or whatever. We'll be able to tweak this, but what I want to do is put it inside here. Now, if I didn't do that, I can just put a variable like 10 or something like that, and you'll notice that as I play this, oops, I'm sorry, I'm in the wrong slide. Decay, I'll just put this up here, but down here in our math.exponent t, I'm going to multiply this, let's say, by 10. Now you can see that each vibration moves a lot, decays a lot faster, because again, we are amplifying that time factor. So over a standard time takes a certain amount, time from 0 to 10 is 10 seconds long. But if we sort of amplify that time, according to this exponential function, is now 10 times as fast. So this whole thing progresses 10 times faster. But again, rather than using fixed variables, or fixed numbers, I should say, let's use variables so we can actually tweak that as we need. So now we have sort of a stiff hand in there. If we want a little more floppy, we could set this to something lower. So that now if we want it to oscillate more, we could set this amplitude higher. If we want it to move faster, we could set this frequency higher. That's a bit extreme. So I'm thinking fairly stiff, maybe 8. There we go. Actually, I got the idea from this by pulling up my clock one day, and I saw this second hand going around, and I saw it doing this exact same thing, and I thought, hey, that is an interesting exercise. And I started on it, and I thought that's actually a good idea for our first class, because what this does, what we just did, was we covered some very simple topics. This plus that. Time times this. And then we got into a little JavaScript stuff where we said, well, just take this value and round it to the nearest value, or round it down to the nearest value. And that was easy enough. Now, all this stuff, when you first saw it, probably looked pretty complicated. But over the course of this lesson, we took this whole thing apart. We went into what a sine function does. It just goes up and down, up and down. And then we added some stuff in here just to control it, to make it move faster, and then actually move more accurately. That's what this 2 times pi is here. But again, that doesn't really have to be there. There's really no loss of just taking that and simplifying it. We would just have to greatly increase our frequency. And then the amplitude, how far it's displacing in each direction. And then we divided that by a value that starts very small and increases. So this divided by this results in a sine function that decreases over time. And we put some more controls in here so that decay of the sine, or the decay of the, I should say that the progression of the exponent value moves faster or increases faster over time. Because that increases faster over time, this is divided by that, the whole thing decreases. And we're adding to this our time progression. We could actually just put this down here if that makes things look a little easier to digest. We could say math floor time times 6 and do it that way. But anytime something gets longer than this, like, I don't know, longer than 6 inches, I guess, is my kind of rule of thumb, I start to try to put variables. In fact, we could assign variables to this and this if we wanted, but I think this is just fine. So, handy little lesson. I think we covered a lot of stuff. If you're new to expressions, you might want to, feel free to watch this through again if anything didn't make sense, or if something just didn't make sense at all, please hit me on the forums. That's what this is all about. But I want to try to, progress through this course, offering up stuff for everybody. And I know this is a bit to take on at first. There's nothing that I went through that isn't unsuitable for a beginner. We just covered a lot of stuff. And I wanted to do that because I want this course to move quickly, and I want there to be a lot of stuff for people to learn. And I want to push you and challenge you and make you learn and learn and learn and learn. And expressions are great things to use. We should all be using them. And so that's a good start. So next week we will, actually I don't really remember what we go into next week, but I've got a lot of things planned. Consult the course guide. This is sort of our introduction week, and then we'll move on to bigger and better stuff next week. In the meantime, I'll see you in the forums. My name's Harry Frank. Thank you so much for watching.